Imagine you're in a city full of intersections, roads, and destinations. You need to find the quickest way to get from point A to point B. But how do you do it? Welcome to Navigating the Network, a journey through Floyd-Warshall. Before we dive into the solution, let's understand the problem. In computer science, this city is a graph. The intersections are nodes, the roads are edges, and the time it takes to travel each road is the weight. Our goal is to find the shortest path between every pair of intersections. Enter Floyd-Warshall, our hero for today. This algorithm calculates the shortest path between every pair of nodes. Let's see how it works. We start by creating a matrix that represents our graph. The rows and columns represents the nodes and the values represents the weights. Initially, the weights are the direct distance between the nodes. If there's no direct path, we use infinity. Then, we start the war. For each pair of nodes, we check if there's a quicker route through another node. But before we dig deeper to our topic, let's first know the history, time complexity, and definition of Floyd-Warshall algorithm.
The Floyd-Warshall algorithm is named after the two computer scientists Robert Floyd and Stephen Warshall. It was first established by Stephen Warshall in 1962 and then Robert Floyd independently published it in 1965. The algorithm is a classic example of a dynamic programming and it's used to find the shortest paths between all pairs of vertices in a graph. It's especially useful when dealing with dense graphs where there's a direct edge between most pairs of vertices. The time complexity of the Warshall algorithm is all V circumflex tree, where V is the number of vertices in the graph. This is because there are three nested loops, each iterating over all V vertices in the worst case. The space complexity is also all V circumflex tree as we need to store the distance matrix during execution. The Floyd-Warshall algorithm is a graph theory algorithm used to find the shortest path between all pairs of vertices in a weight graph. It is an extension of Weierstrass algorithm which can only find the shortest path from a single source vertex.
Now, let's dive into the heart of the battle. This war is a contest of paths, each trying to prove that it's the shortest. It's a process of constant updates and improvements until we find the quickest route for every pair of nodes. Let's consider a simple graph with 4 nodes, A, B, C, and D, and the following edges with weights A to B with weight of 5, B to C with weight of 3, C to D with weight of 1, and A to D with weight of 10. At the start of the war, our battlefield looks like this. The numbers of the edges represent the initial weight or strength of each path. The first round of the battle begins. Our warrior A steps in. It checks if it can help any pair of nodes reach each other faster. And indeed, it helps B and D, reducing the weight of their path from 13 to 10. Next, Warrior B enters the fray. It checks for any path it can improve, but in this round, B can't offer a shorter path than what's already available. Then, it's Warrior C turn. C manages to find a quicker route for A to reach D, reducing the weight from 10 to 9. Finally, Warrior D steps in, but at this point, all the shortest paths have been found and D can't make any further improvements. And that's the end of the war. We found the shortest path between all pairs of nodes. Each fought bravely, but in the end, the quickest routes emerge victorious. This way, you're making the process of the Floyd-Warshall Algorithm more engaging and relatable by framing it as a battle.
And that's Floyd-Warshall for you. A powerful tool for finding the shortest path in a network. Whether it's routing internet traffic or navigating a city, this algorithm has got you covered.